So, anybody want to say something, or what?
Did Yamo have an announcement?
I don't know, Yamo, you have any announcements? No.
Not bad.
Huh?
Yamo was looking bad.
At the end, okay. And the end will be when it's ready to be the end, okay. So again, the idea here is to stimulate the interaction and see if we can come up with some deep insights that who knows where it'll lead. The two biggest things I got from yesterday, actually, three biggest things I got from yesterday actually was the 3D notion that how we gonna, what is 3D gonna mean for the future microprocessor? The notion that the memory is really gonna be, chip will be 80% memory, maybe 90% memory, 10% processor, what does that mean? And this deep insight that I think was a deep insight that Manolis provided with respect to the organization of lots of, I don't know, cooperating entities, and in particular this notion of transferring data with a granularity that makes sense. But and having software have a say in that transfer. But that's just my simplistic set of three things I took away. And I'd like to just, so, any of you guys want to?
I got a question for you.
Okay, a question for me.
So one thing.
He's up all night preparing.
Yeah, yes, right. You're a big fan of instruction level parallels. Where's it going? It seems to have ground to a halt. Would you say?
No.
Explain why not.
So, I guess my favorite example is the penny mem chip. So the first generation of penny mem chip was 77 million transistors. 50 million of them went into the L2 cache. The second generation, instead of having 77 million transistors, they went up to 140 million transistors. 110 million went into the L2 cache. Performance benefit was 5% from the first to the second. So you double the number of transistors, 77 million to 140 million, double number of transistors. The performance benefit is 5%, therefore ILP is dead, right?
No.
But if you subtract the numbers, 77 million minus 50 million is 27 million, and 140 million minus 110 million is 30 million. Most of the transistors didn't go into the processor. So why do you, so the processor is what ILP is about, and if you don't give it the transistors, but then you blame it for not taking advantage of the double. Okay? So that's my first point. My second point is that one is never going to get the benefit, let me say it this way. In fact, I think it came out somewhere in the panel yesterday, is the higher up you go in this transfer, what I've been calling for the last 30 years the higher level, the transformation hierarchy. Now they call it the software stack, I guess, because you can't use my term because that's not allowed. The higher up you go,
I don't think they're just picking on you.
well, so I'm paranoid, like Candy Grove. The higher up you go in the transformation hierarchy, the more benefits you're going to get. So if you improve the microarchitecture, you get a factor of 2. You improve the compiler, you get a factor of something larger than 2. You improve the algorithm, you can get a factor of 1,000 or something. So what I'm saying is don't use the same metric for ILP, which is a function of the microarchitecture being able to handle it, with what you get from the higher level, the algorithm. Change the algorithm and, you go crazy, right?
So maybe some members in the audience have some thoughts. Who thinks that instruction level parallelism has had its day? Who doesn't think it has had its day? Who thinks there's more instruction level parallelism that could be gainfully used in future microprocessors?
I think ILP still has its uses. It's not the general solution. But if we go to a heterogeneous multicore, cores, then one of those cores will be an ILP core. Maybe not the other ones, but at least one of them should be an ILP core. Because when there's nothing else, that's what we know how to do well. Okay?
Well,
if the algorithm is not parallel, if the programmer was not wise enough to expose threads, if there's nothing else, what we're left with is with microarchitecture and ILP.
Okay.
So why not
I
go
think
further?
the question, though.
So why not go further than that? Say-
I'm more interested in, not a statement like that, but more, where is it gonna come from? How are we gonna construct more instruction level parallelism? Why have the commercial chip designers at least pretty much maxed out at 3 or 4 in the top end machines?
Power 6, Power 7, that's not 3 or 4. It's between 5 and 8 instructions per cycle. I mean, if we're looking at Intel cores, if we're looking at AMD cores, yeah, 3, 4, that sounds good. They're not the only ones out there. And there's VLIW architectures out there, the Trimedia 3280, I think had 8 instructions per cycle.
Yeah, no, I mean, but they are application specific things. I don't, there's no reason that you cannot.
So I won't even concede that Intel processors are maxed out. We're not, a better branch predictor. To go from 98% prediction accuracy to 99% prediction accuracy, we get more than a factor of 2 in performance. We don't know how to do 99% prediction accuracy yet. There was a time when we didn't know how to do 80% prediction accuracy. And in fact, there are a lot of people that.
But you've not only got to be able to do accuracy, you've got to be able to do it economically. Otherwise, you might as well go out and build another core. I mean, if you have a massive machine calculating the prediction, like some of the recent proposals for branch prediction, it seems to me, just looking at them, they actually require more gates than the core does. It's like, this is silly. This is standing things on its head.
So I don't know that it is silly. If we have 50 billion transistors on a chip, we can afford to have a.
Why not just have 2 less efficient cores?
Because they're not going to do
it. To run on the second core.
Exactly. Plus the fact that how often do branches show up, So let's say, what's our issue with? 4, 8? And so there's going to be a branch there, so the next cycle it goes this way, and I need 2 cores. The next cycle is going to go this way, I need 4 cores. By the time the branch is resolved, I need 2 to the whatever number of stages I have before the thing is resolved. And only one of them is doing useful work. So.
And I think I'd like to remind everybody of my little formula from yesterday. That took energy efficiency and the cost into account. And I think the reason IRP isn't going up is because it's not efficient to do so. You're throwing more stuff at it and you're getting marginal returns on your investment. The bottlenecks in the system are elsewhere. Today, IRP is not the limiting factor.
That's sort of like
it's the memory system, it's how you coordinate the movement of data. It's not about how you coordinate the pipeline. And yes, you can design things with higher throughput if you want to, but I doubt that you're going to match the requirements posed by my very succinct form.
So let's separate out memory from processing. I absolutely agree. In fact, that's one of the things I think to take away from this panel is, maybe your comment yesterday, 80% of the chip is memory. In fact, I don't know that I'm going to do a plug for Wallach, but Wallach, was convex, right? Now they're convey, because Y comes after X in the English alphabet. His next processor will be convex, I guess. Z coming after Y. So convey, if you look at what they're doing, most of their energy is in speeding up the memory accesses. So you may want to look at what they're doing. But, so I agree that memory is important, and in fact may consume 80% of the chip to try to get memory right. But there's also processing. And the fact that memory consumes so much of the chip, now what do we do with the processing? We do Mickey Mouse? Or we introduce these other things? There are places, in fact, Alex said it, he says, what if I didn't like the way he said it, because he said, what if the programmer can't figure it out or something or other? Take your most parallel algorithm. There's no Amdahl's law bottleneck in it. Take these multiple threads. There's no critical section that you want to go fast through it.
Yeah.
So that's why you need that single core.
You need some, agreed.
Yeah, and in fact, I would argue, by the way, one of the things we've discovered is that one core is not enough, because, so, critical sections, for example, if you have one high-performance core, it works on a critical section. What if you have another critical section, it has nothing to do with this, then it has to wait for this core to get through with that other critical section. So, my guess is probably gonna end up with, I don't know, by the year we're talking about, say, 1,000 cores, maybe 2 or 3 of them will be heavyweight, I don't know. But do we ignore that? Do we just grind to a halt?
No, I'm not saying ignore it. I'm just wondering what that heavyweight core is going to be. It may just be an overclock thing that gets its performance back.
I think it's going to have a branch predictor. It's going to have a serious branch predictor. It's going to be wide issue. It's going to have accelerators hooked onto it to do pieces of work that you can characterize at the algorithm level to, you know, an ASIC to do a particular task is always going to be better than a...
I mean, the higher issue machines, think about the Alex, actually have had the very, you know, first of all, they're not used widely. Secondly, the designs that have been in that direction have failed more often than they've been successful. Because there's another issue with that. There's just the complexity of the design and the problem with validating. You can't spend 10 years designing something because you're 4 generations behind by the time you've got it done. So you've got to have, you know, it's pretty difficult, I think, to even, the validation issue is a real barrier. It's not just...
So I think Manolis mentioned breaking the layers between the levels of the transformation hierarchy. So why don't we design microarchitectures paying attention to what's needed for validating them instead of doing it as an afterthought?
They kind of are designed that way.
Are they?
Yeah, they make very strong trade-offs on features and how easy it is or difficult to validate.
Then why is it that Intel, for example, tells me that if we could come up with something that would make that easier, as you know better than I do, that if you see a design bug far down in the pipeline now producing the chip over time, that pipeline.
Yeah.
The later you see the design bug, that's right, much more expensive. So the word I guess
that's not quite true. It has to be a bug that you can publish in the New York Times, like to be buying. Whereas if it's something like, you know, some bus protocol that doesn't work right, no, it'll never work. Nobody will know about it except the poor guy that tried to design it.
You know who discovered that bug, by the way?
I don't know.
Really? A Michigan undergraduate
Okay.
having a summer job at Intel.
It was good.
But so if the design bug is
That's
found,
really not hiring.
huh?
That's why they're not hiring anybody grads.
That's why they turned off the no, so right. So a design bug found late is going to be problematic, right? So you're right. Validation is an important problem. Why don't we break that layer and have microarchitects have a clue as to what it takes to, validate?
No, I'm just right. I think it's fair to say that there are not very, that ILP has. Hey, there was a time when you were saying 32 wide issue. Yeah, I can remember you standing.
16 wide.
You see what I mean? Rewriting history.
No. I still say no. I still say 16 wide issue.
Well,
when we came up with HPS in 1985, we were saying 4 wide issue. What do people say? There's not enough parallelism. It makes absolutely no sense to ever build a 4 wide issue machine. And first of all, there's not enough transistors that's going to be able to find the parallelism to make that happen. So there will be no 4 wide machines. Everybody was laughing. So I can't get. By the way, I can't get my students to work on 16 wide issue. They think I'm crazy.
Yeah, finally.
Which is problematic. Because if you don't push the envelope, you'll never get there.
Well, it can it is a fact that whole program of discovering instruction level parallelism has tapered off. Do you agree?
I think it's tapered off because there are too many gurus.
I'm not saying that there isn't instruction level.
I'm sorry?
I'm not saying there isn't.
There is.
There must be. Well, you're more or less saying that as an act of faith, because where is, give me an examples where you can efficiently use a 16 wide issue, not VLIW machine that's running, or simply it's running.
No. So we're not talking, no, absolutely. We're not talking Sydney, we're not talking
So my thought is,
VLIW.
there is a wall there, and maybe there is a solution to it that nobody's, some genius will come along and say, look, if you do this, suddenly you unleash another order of magnitude in instruction level parallelism. But I think that's what it's going to, it's either that or it's not possible. Because I think the conventional techniques that you've seen in the papers written over the last 20 years, they've sort of run out of steam. I mean, I think a lot of these guys that write these papers, they have to sit down and draw the logic diagram on a piece of paper. And they'd understand why you can't do things like that.
So we do that, actually.
Okay.
No, we do. So we don't carry it through to the end, but we do make the back of the envelope logic design to see whether or not our
I mean,
ideas,
the complexity of some of the
see whether our ideas
structures
hold water.
defy gravity.
Huh?
I said the complexity of some of the structures that needed these things seem extremely difficult to build.
So Trevor, while you're at it, what are your least favorite papers from recent years?
The ones you wrote.
Aside from your own, yeah.
Yeah. No, seriously. I mean, I think what other techniques are we going to apply to that we haven't already? So you're saying, okay, what we need to do is improve price prediction. How are we going to improve price prediction?
I have no idea. But if I tell bright graduate students that it can't be done, then we'll never improve.
But the thing.
So when we came up with the branch predictor, people had already said it can't be done. And we did it.
Well,
why?
I'm
Because
not sure
we
that's
leapt
true.
onto it, okay? So we did something, we saw something.
I
and we
think
said-
people saw the immediate value of that, and I don't think that people saw it.
But I think, I mean, people have written these papers on value prediction and all that back in the 90s that show that if you could actually do those things, IRP would go up. I think the problem with a lot of those ideas is that nobody knows how to implement them, or they actually disagree on some of the figures. But there are things that you could do that do memoization. They do things that you do in a general virtual machine, except you try to do it in a microarchitecture that potentially could unlock IRP. But the feasibility of them is quite large, and I think that is unknown because nobody knows how to build them. But I think just pragmatically, usually when we reach to a point where things become that difficult, it's usually just easier to look elsewhere for the solution. Right? I mean, I think your idea of breaking the abstractions is a good one. And usually there are big payoffs there, but, so go ahead.
Exactly, so if I can break here and also give the opportunity to pair also contribute to this discussion, because it's like, 1-2 between Trevor and Yale. Indeed, Chris, I agree. The breaking the layer is probably the issue. Since, Trevor, indeed, maybe we try to fix a problem that we created, right? We program sequentially, compile sequential code, and then try to extract instructional parallelism out. Of course, they may be not very easy to do so. What about indeed try to identify parallelism? I'll quickly parallelism at the very early stage, because there's a lot of parallelism in algorithms, right? So there is no disagreement about that. Then pass this information to the hardware, which will simplify the hardware complex structures that we are referring to. And this will avoid of first getting rid of this parallelism and then trying to recover. So, and Patt does work in that direction in his startup company, so maybe we can say something about that.
I mean, so this discussion about IRP exploitation, I mean, Alex was mentioning that, that's still important because there are serious sections in the code, but the big problem for me is, why should it be easier to extract instruction level parallelism in those serial sections? Is it because, it's there was a parallelism that we have forgotten about, or I fear that, ILP the ease of exploiting ILP exploitation goes hand in hand with the ease of exploiting coarse-grained parallelism. Let's take numerical loops or something like that. It's possible to do ILP exploitation as well as coarse-grained parallelism. But are they really bringing complementary values? I don't know about that. So I think we are in a situation we have tried to exploit even TLP, Thread-level parallelism, automatically. I've done a lot of work on thread-level speculation, and I think it's fair to say that it hasn't taken us far. That bulk of research that has been done on that. So to me, I think the world is such that, I mean, we cannot do this at a hardware level automatically. We will have to break the layers. But architects obviously have to provide, ways to unlock the parallelism, so the task of exploiting it at higher levels become easier.
So I don't think that we've forgotten about the parallelism or something. I think that it's there. It just we're not able to see it. How about if we could do a data flow graph? The data flow has been around for a long time. We never built a data flow machine. I would argue that every out-of-order processor is a data flow machine.
We did build that.
Well, in Britain, that doesn't count. So Manchester data flow machine ran like a dog. The Utah data flow machine, I don't know that it did a lot better. But to try to capture the whole program as one humongous data flow graph is very, very problematic, right?
No kidding.
Yeah, but maybe the stuff. The data flow. The guy did his thesis in data flow.
Exactly.
All my life in data flow, I don't do anything.
Even now, huh?
Yeah, I'm just.
So go ahead. Interrupt.
Basically, it's actually I will just quote other people because no one.
I'm sorry.
I'll quote some other people because no one pays attention to people from small islands except SAMOS. He's the only one. So basically, I was happy when we put. Oh, sorry. I'm laughing. When I listened to when people from Illinois putting a slide saying deconstructing von Neumann, and that basically what we're doing, writing a sequential program, and they were trying to make it parallel. And that's schizophrenic. As a concept, why we still write sequential programs? If we put, I believe that if we are putting the effort we put in making this out of order and all those complex structures and everything to really change the model of execution in parallel, we would have solved the problem. Because it's not that difficult. We have to remember that when David Kahn was still doing the science of compiler, it was the best parallelizing compiler. And he was doing something that was single assignment. So it's not very difficult to build a huge data flow graph. You can even handle cases with pointers and stuff like that if you do it right.
So why did it never play out?
Because the industry, and basically, and that reflects the opinion of the panel, because we keep insisting on how to do what we've been doing up to now. I believe that nowadays we see a lot of movement towards single issue processors, power efficient, and putting more of them. And I believe that eventually we're going to get there. We cannot continue like this to ignore that we have a problem with memory indices, and the way we are creating the procedures which are sequential is just something that when no one thought 70 years ago, it doesn't mean that we have to continue doing it the same way.
So go ahead.
I mean, I'll give you an example, like high-speed trains is the best way if you have flat and you can make them, but you cannot put them in mountains, you cannot put them in places that they turn a lot, etc. But we still, in chip design, we still try to just force the same design.
But the difficulty is dynamically building the dependence graph and detecting the dependencies in the presence of pointers, isn't it?
Depends how you handle it.
Are you doing it dynamically or are you doing it statically?
Okay. Basically,
Seisel's not doing it dynamically.
Oh no, it's done as a compiled. I mean, it's done. I mean, if there are no pointers, pointers are okay. what is the pointers is that when you need to chase them through, many locations you don't know, it's difficult, but it's not impossible. We are actually working on that right now, but it can be done. I don't see, why you cannot do it. The compiler technology is there. It's just is not used because we put emphasis, like we hire someone to help us with the small compiler project I mentioned in my presentation, and he discovered there are parts in the GCC that people put for parallelization that no one is using. So we're trying to explore those. Actually, I'm trying to have some early wins, so I just decided to concentrate on vectorizable code. Not only the ones that they were vectorizable at the days of Polyphonopoulos and other guys, but even the ones that they discovered as a data dependency and they couldn't fix it, because in a model like ours, that can be handled. So, but anyway, this is, I'm happy to show you, how we really do things, and I think it's going to be easy to implement both at the compiler level, at the architecture level, the changes.
But I think figuring the flow graph isn't really the problem that is limiting parallelism today. The latency and actually the communication of those little blocks is a limiting factor. If you look at an out-of-order machine which is trying to do a very similar type of a wake-up on when the data comes available, historically people did that, they waited for the token and then they fired the instruction once all the data was there. Turns out the latency is too large for that too, so you have to speculatively do it. And you're firing these instructions speculatively and then you try to resolve it later in the hour. So I'm not sure whether it's actually the right problem to solve, because I think a lot of these machines do a lot of, they go very far to discover the dynamic dependencies, and what ends up limiting them is actually the data communication, not the fact that they don't have enough of these dependencies around.
So maybe the problem that you're exposing, or the problem that these machines had, was a granularity issue. Okay, going back to what Manolis' point was, maybe it's not that I have to send one data element for the data flow, is that I have to send a whole block, something that's of a reasonable size. So the latency no longer matters.
And I think Yale has quite a bit of experience with those block-based ISAs that try to work around those things too.
No, I'm thinking of something even bigger than the block-based ISAs that Yale was 90.
So then you can definitely move up the granularity and packetize it and solve some of the problems. I'm just not sure if these are actually the bottlenecks preventing you from achieving higher levels of parallelism. I think at some point you have to transfer data, and at some point you don't know exactly which dependency is going to be. You're going to have to be speculative anyways, even at that granularity. And it's just hard to handle speculation. You take a look at the amount of state in these transaction-based systems that are trying to solve that type of a problem. When they speculate on a lock or they speculate on a transaction, you end up with huge amounts of data sort of exacerbating the problem that limited your parallelism in the first place. By the way, the other thing I was going to say, sorry Manolis, I'll let you speak. I think there's this other weird thing about sequential code, and I think there was it's actually efficient because it's a form of compression, and if you look at control dependencies, it's a bespoke compression of a piece of code. And a lot of people have made the argument, okay, well you write things in parallel, and you may be running more instructions. And then it will run in parallel. But I think, actually even the DSP, where a lot of the arguments are going back to much more control-dominated type of algorithms, because it ends up being more efficient to actually run the algorithm. You run fewer instructions, you have better control of the communication patterns and the control patterns. And I wonder what the implication of that is. It is the thing that we're not good at doing anymore, because we've run out of technology scale for the time being. And yet, even from the efficiency point of view, those are the things that people would like to do. Sorry.
Well, I'll go back to the previous discussion about granularity because it allows me to say what I wanted to say, and in fact what I was preparing to say since yesterday with my position yesterday. So, in our work within a European project which is also related to the dependence graph and the sort of data flow, we are looking at higher granularity dependencies, higher granularity in this dependence graph, entire tasks. And the data that those tasks manipulate, well, in case they are arrays, you can decide on the size of the blocks of the array that you are going to manipulate and detect dependencies, and it looks like it works fine. However, when there are random pointers, what I call random pointers between small data structures, then it looks like things are difficult. And that triggered me to consider the following thing, Since several decades ago, the database community discovered and developed specific data structures and algorithms that allow them to do searching and sorting and other operations on disk resident data more efficiently and differently than, different algorithms that are more efficient than the algorithms that you use if the data are in main memory. So in main memory you may have a binary tree where each node of the tree is a little data structure of a few words and you search it efficiently. However, if the data are on disk, you don't do that, you do a B tree, I think they call it, and it is differently structured, different insertions, deletions, and different search algorithms. And it works more efficiently when you access data on disk. So, for me that is an example of the fact that when an application is important, you have to look at the constraints of technology, and people put in the effort to adapt the data structures and the algorithms to the constraints of the technology. So I think that today we are with multi-core and massive parallelism in the hardware, we are in a similar situation where there is a lot of difference in access time between local memory and remote memory. There are a lot of situations where you take advantage of larger granularity. So probably we should stop in such systems, we should stop programming using data structures that manipulate random little data structures with random pointers going anywhere in memory, regardless of locality, and develop and use new data structures and new algorithms that put together inside the same block, inside the same locality, multiple of those little things. With pointers being internal inside the block and pointers being external, and these two things being handled separately. Pointers that are internal to a block are less expensive, pointers that are across blocks are more expensive, so you use them less. Okay, sorry to change the subject, but...
So I have a question, this is interesting. So in your opinion, has the access ratio to local or remote memory changed over the last, let's say, 1 to 2 decades? If we look at SMP machines, or is it basically the same access ratio to local versus remote memory? I'm wondering, has it really been a big change now with multi-cores? To make this problem,
if we do nothing, it is not going to change. Perhaps we should do something for it to change. For example, why is the number of processors you put on a looping bus protocol, why is it up to about 8? Because 5% of your accesses are to remote data that don't fit into your cache, so you generate fast traffic. And that has to go down in order not to overload the directory, for example, the continuous directory, or not to overload the network on chip.
So I think I'd answer your question with Manolis' earlier point, which is that we need to change the algorithms. The access thing is going to change if we, in fact, that's a fundamental thing. If you look at what the underlying structure is and you develop new algorithms based on what that is, it'll fall out.
Or maybe the volume of the local data to remote data may not change. You may always need a lot of data to perform a lot of computation, but the number of transactions to get those data has to go down. Those transactions have to operate on larger volumes of data. like when shipping from China to here, you ship in big containers, not in little bags.
So I agree with that, absolutely. So my question is why didn't we discover that 10 years ago? That's my question. Because I don't think that the access, I mean, obviously the speed gap is probably not going up anymore. Clock frequency scaling has stopped. So my question is, did we have pretty much the same problem with the SMD systems, or is it just that now it becomes mainstream, so now this problem is probably more...
Because it's hitting us over the head. So, you know, I do want to, so at the risk of promoting one of our pieces of work, the ISCA paper that we had this year, said, the data marshalling, that's right. So with the data marshalling, you say, okay, here's this thread that's working in one of the little cores, and now it hits the critical section. You want to move it over to the heavyweight core, right? So there's private data when it was working, and now the critical section is, in some sense, well, shared data, clearly. Public data, maybe you want to call it. Shared data is probably the right word. And so when you go over here, the shared data takes no cache misses, because the shared data is on the heavyweight core, and it's available to all these little threads that go there. But now what about the private data that you now going to get, if you work here, now the private data is going to cause cache misses. So what do? We figure out how much of this is going to be needed in the critical section, and we ship it early. So I'm kind of, you know, impressed with myself about that. That we have, if we left it here, we're going to get cache misses on the heavyweight, we're going to have okay on the private. If we move it here, we're going to have, you know, on the shared, we're going to be okay, but we're going to be bad on the private. No, Manolis' point. You can, ahead of time, ship what you're going to need when you get there, and then you win-win, rather than have a choice of win-lose versus lose-win. So it's a new way, so I don't know what's a new way. For us, it's a new way of looking at how to take advantage of the fact that our engine is one heavyweight and all these things.
Yeah, no, I agree. So I think that, I mean, these problems were also worked on in the 90s when distributed memory machines was a big topic.
So I think now...
So what has happened is now these problems has moved on chip, right? Is that
and so it's moved on chip, and there's so many, so it's now hit us over the head that what are we going to do? We've got to do something. So, no, your question is right. So why didn't we solve the problem 20 years ago? You know?
Yeah, but,
because we didn't have to.
We didn't have to because it was not an issue
right.
for the chip, right? Yeah.
Right.
There was a question down there.
Yesterday we had in the equation we also had money somewhere, and I feel like many companies close the fabs, and for example, transition in microarchitecture is risky, so a company will not do it because of money reasons. And software is, there's a lot of existing software, so how much does it cost to change it? So my question is investment, where should it be taken first to come to the next step? So this is my question for you. So where should we make an investment? Because everything is risky and everything gets expensive, and the citizen doesn't
And of course, and of course I don't care. Because I'm not interested in making a buck. I'm interested in coming up with a chip 10 years from now that's going to make sense.
You have to
And if your company goes out of business, well, you know, you can always, you know how to drive, you can get a job driving a taxi.
No, I can rephrase the question, make it economic neutral.
I'm sorry?
I make it economically neutral so that you may be interested or thinking about it.
So I don't know what economically means. So Chris, you know, hits right on target is that you can't come up with this idea that's going to just...
No, listen. So you have a bunch of bright students.
Right.
And you want to ask them to work on something. And you can decide between microarchitecture or some clever software transformations or new algorithm development. You know, what you would choose of this particular model. So, this is basically the same question, right?
Yes.
But more money involved.
Yes.
More money.
So first of all, I don't tell my graduate students to work what to work on. I already wrote my thesis. It's their job to find their thesis topic. That's number one.
What to advise them?
I do tend to, in my very subtle way. So, you know, to go full circles, I do want to close out of this thing with Trevor, is that I'm not suggesting that 100% of the effort go into ILP. That would be stupid. But what I am suggesting that it is not the case that 0% of the effort go into ILP, which seems to be the prevailing sentiment. Because, you know, economics and efficiency and, you know, all this other stuff. I don't know. So maybe you guys want to take a crack
I have
at
an
advising
answer.
your graduate students or something.
I think, I mean, you know, if you wanted one tagline, I think basically we have to be in a world 10 years from now that thinks of an SoC as if it were a microprocessor. In other words, it's consistent in detail, it knows how to use all the resources on it, it has the right software abstraction. Because I think what we're going to see over the next 10 years is that building SoCs that has been done by a few people is going to go, basically every processor company is building SoCs today. And the solutions that people have come up with while the SoC was kind of an embedded concern, you know, they kind of work, they're not very scalable, they're kind of ugly too. You know, a lot of software people have to patch things together to make best use out of these SoCs. That's the problem. These heterogeneous things on, you know, with not enough architectural content probably, used in ad hoc ways. How do you turn that into something like the microprocessor that people can actually program? It has an evolutionary path, and that's what I would say is next 10 years progress. And yes, it has an ILP machine on it somewhere, and it has a graphics processor, it has video, it has a bunch of accelerators, it has a whole bunch of hierarchical memories, and you're a software programmer, please make use of it. Yeah, that's the problem.
My personal impression is that we try to answer here questions that can't be answered with a single answer. We can discuss as long as we want, because it's always the same. I think improvements are coming on all the levels, down from circuit level up to the algorithmic level, up to the system level, to new applications and so on. And a little bit more ILP or less ILP, a little bit more different architecture concept, different circuit concept, different influence of technology and so on. I think it has been the same since 30 years. You have to improve everything, and it has to interoperate. So there will never be a single answer what has to be performed. If it's more software or more hardware, it's everything.
I think I agree that you have to look at all those things, but where I disagree very strongly, no, the circuit and the technology isn't improving. It's falling apart. So I think it really changes the dynamic of how you're supposed to be solving things. You know, you can't rely on that. You know, in the 90s, we got a factor of 2 power improvement, factor of 2 speed improvement each generation. Today, you're getting, you know, a little bit.
I know that. The technology changes, but then we have the feedback to circuit level. For example, think about things like grid design and so on, which came up in the last years. I don't think that the circuit improves, but on circuit level we have also to find answers. Grid level design.
Yeah, but the magnitude of those improvements aren't large. So basically, you're staying flat at best with the circuits.
Yeah.
And therefore, you actually have, the architects have a harder job. You can't just dream up new structures because you don't have the power budget to actually put them down.
Yeah.
I think it fundamentally changes how you have to approach the problem.
Yeah, but it also means that we also have to do things, for example, on circuit level as well as on the higher level.
Agreed.
On all the levels.
What has also happened is obviously, you were saying technology is falling apart. I would say the sequential programming model is also falling apart. I mean, also that's a new challenge, I guess. I mean, that computer architects cannot work so much in isolation as we have had luxury to do. We will have to really provide, you know, much more effective primitives to the software to make use of it to address this big programming model.
So I certainly agree with that. You know, that, I mean, that's breaking the layers, getting these more complex primitives, which I would say are accelerators or whatever. You know, the AMD came up with a chip called the 29000. It was such a silly RISC chip. You know about RISC chips, right? Yeah.
I happened to consult for AMD when they were designing the
29000. Yeah, good. So they wouldn't even do a load. So you know that a nice RISC, whatever RISC, I never figured out what RISC meant, but load register with from memory you compute the address in that instruction, and then go to memory and load it to register. AMD didn't even do that, see? If you wanted to load from memory, you had to do one instruction to figure out the address, put in a register, and then the load instruction would look in that register. So it was the RISC, you know, the simplest one operation per instruction. That chip, that ISA, had a find first instruction. So you had a bit vector, and what the instruction did is looked at the bit vector and found the first bit that was set. Or another one, the first bit that was clear, it doesn't matter. So try to do that in software. You know, you look at the first bit, and if it's a 0, well, I gotta look at the second bit, and so you branch back to shift 1, and then look at the first bit, and if it's not if it's a 0, then you branch back and you shift 1 bit, and it'll take tens of cycles to get that simple, find the first bit that's set in the bit vector. Do it in hardware. It's a priority encoder that every sophomore has designed in the digital logic course, fraction of a cycle. What's my point? That there is a piece of functionality that maybe you're the one that recommended they put find first into
I don't
ISA.
remember anymore. I don't even remember that thing with the address.
You don't.
Was that to have
See,
compact instructions?
I hope,
only?
yeah, so I hope when I get to be your age that my memory doesn't fail the same. So the point is that tens of cycles to get the job done are a fraction of one cycle. And they thought the primitive made sense for lots of applications, and so they stuck it into the ISA, which is what you're saying right there. Yeah. I think that has to happen, and I don't know, somebody else's turn.
So let me ask you a question. In what ways is sequential model programming breaking down?
Well,
I mean, can you give me case? Write a program that's broken. I know.
no,
That's easy.
from a performance point of view, that's what I mean. I mean, in
Okay.
order to...
I thought you were saying there's a way to conceptualize algorithms or something.
No, I meant more, I mean, the way to get the performance, leverage on the performance from chip. You have to...
Have a different programming paradigm, maybe data flow.
That's one, I don't know. Maybe. Yeah, well.
A question. If I look at the software, and I would classify it along, it's not like affiliated. So I see applications which are computation intensive. They are sort of the scientific applications that do real work, perform real calculations. And I see applications like someone mentioned yesterday, PowerPoint, that for some reason is slow. And well, for most people's computers, essentially we're trying to accelerate PowerPoint because the large mass of people is not trying to perform scientific computations on their computers, except maybe as a hobby running SETI at home and what else. Now, within this application, I would argue there is plenty of parallelism. I mean, what does PowerPoint need to do, or a web browser? It needs to parse a couple of 100 kilobytes of text, which is really nothing at the speed of processors today parse the text, and to display on the screen some independent images and letters, which probably you can even split the letter into pixels and display them the pixels at the same time, but if not, you can at least display row by row or phrase by phrase, and you can do that in parallel. Obviously, this is not done. Now, I see the challenge differently because these are programs that have hundreds of thousands or millions of lines of code. So now, I don't see it as much as a problem of the processor as I see it as a problem of the software.
It's difficult, by the way, it's difficult to display things in parallel. What you said there, actually, if you think about it, is that you want an output device that you can write to broadside. You're talking about something that's got some massive bandwidth. That's why it's not done.
No. Just back on the level of computation, if I'm just interested in displaying one screen of information which is 3 megabytes. I can do that in 0 point something seconds.
I mean, PowerPoint is actually bottlenecked on the memory system. It's not a parallelism problem. They're using huge amounts of data in very inefficient ways. If they rewrote their code to actually access data more properly, they'll speed up significantly. That's one answer. But the other one is you can use Keynote.
Okay, so I would agree with you. It is done in very inefficient ways. So then the problem we are trying to solve on the processor side is how to deal with the inefficiencies of software, not how to accelerate computation in itself. Maybe we can...
Yes, I think I would say that on the sequential, the IRP core problem, it is that memory system problem that I think should be our focus. How do you move data in and out of that thing? We are pretty good at running large number of instructions. The ALU isn't the bottleneck, right? It's how you get the data there to actually do useful stuff. And I think that's where some of these breaking of the abstractions ideas come in handy if you figure out what is the right way to break them.
So, yes, I agree with you. Without knowing PowerPoint, I would guess that it must be written inefficiently. Also, in networking protocol stacks, I think that there is a lot of redundancy between the stacks because complex systems are built on layers and layers of other pre-existing systems or pre-existing protocols. Or manipulating pre-existing protocols so that they do something different without changing them, etc. So again, it is an issue of lots of layers of abstraction where you gain in productivity but you lose in performance, I'm afraid.
So how would you recommend that what should we substitute for the sequential modeling program?
Well,
this has been said for many years, right? People said, well, the problem is the bundle and the problem is. But there hasn't been a credible replacement. And I don't think data flow is different. You're going to need to write a database and data flow.
One possibility, I'm not sure if it should be the central one or probably not the only one. One possibility is that a few people or a few companies build libraries of parallelized libraries for important tasks or important algorithms, and then other programmers just use them.
Or they could be ASICs on the chip. So why isn't Manolis' earlier comment, which is sort of to a first approximation, the CETA project of 25 years ago, I guess, where you take the problem and you have coarse-grained data flow at the top, and then you have a hierarchy, so that you ship. So Manolis' term task parallelism, I forget what Cook called it in Illinois, but you analyze what has to be done into large units. And
macro
those
data flow, I guess.
Huh?
Macro data flow.
Well, okay, so
Something
macro
like
data
that,
flow,
yeah.
that's as good a name as any, fine. I actually like task parallelism that Manolis comes up with better because it captures, I think, the level of what you want to encapsulate as one unit of work that needs to be instantiated when all the dependencies associated with that large unit is satisfied. And now you need a global controller to ship this piece, and then when the results are ready, I can ship these 3 pieces, and etc. Now, shipping the piece, that's step one. Now, what about what's inside that piece? How do we handle that?
But I would say that's not the problem. I think the dependence graph and how these things, I think all these systems even today, if you look at, they express it some one shape or form. I think the problem is actually, the library is the way that a lot of people would like to use it. The problem is the library is don't compose. So you may have one parallel algorithm that kind of works given 10 assumptions. And now you're trying to do something different, suddenly the locking is broken because we don't know how to compose these parallel things and not break them. So the problem is very, you can simplify it. It's about the interfaces and what the language is on those interfaces. And this is a classic problem a lot of people have tried to tackle in software engineering, and I don't think anybody has a really good answer on it. Java had a cracked before there was Corba, and then all these million object models try to do it, and fundamentally we don't know what the language is to compose interfaces. And I think unless we do that, all these library-based abstractions are going to be doomed to fail. They'll work for some limited set of examples, but you're going to spend up enormous amount of resources kind of developing these bespoke libraries. So it's about that composition of the interfaces, I think.
The DSP world does something like Manolis too. The DSP world does something.
Yeah, and it's very domain-specific way. Sometimes you can find solutions.
Actually, what I mentioned in the presentation today, Intel with HP and others, at least Rice University, they came up, they are supporting the CNC language, which basically it maps into task or whatever you call it. The computation can have side effects, but what you don't want to have is the communication is side effect free. And basically that solves all the problems we're talking about, complex dependency graphs, etc. And then you have a smaller grain that you have to analyze and resolve inside that smaller piece of computation. And that's basically what we are doing as well. It's just we are looking at from the hardware and they are looking at from the software. So that is something which will work, because the sequential processing is efficient. No one argues that. So if you isolate a sequential portion, then I'm sure the compiler people will be able to do ILP, they will do anything, they will extract everything, reduce, have zero, pipeline stalls and everything, because you have a small piece of code, a few hundred instructions, and you can do it.
But the problem I'm referring to is related to, for example, how you use locks. When do you acquire a lock? When do you release it?
That's the idea.
So in the CNC,
you have single assigned communication, that means you don't have locks across those things. Those things are local. Those computations are all local. The computation is between the things. So you basically isolate it, and it's possible. I mean, if you look at it,
if you don't have shared data substructures, I agree, things become easier.
But if what we are trying to do in hardware, I mean, I'm going back, I'm reversing Yale's argument. What we're trying to do in hardware, we should be able to be done in software as well. In the compiler, we spend the time with the compiler and give the compiler time to do it, can resolve most of the things unless we on purpose write programs that we don't want them to be discovered with parameter compiler.
So anything to be done in hardware can be done by the compiler. There's no dynamic information produced by the program running that's essential to know what to do next. I guess we could make the cache at the ISA level so that the compiler knows everything that's in the cache and everything that's not in the cache. We could not have branches because branches require dynamic information to know which way the branch went. We could make every functional unit take, if I want to multiply by 1, it takes just as long as to multiply by some arbitrary number. I don't know.
I think I figured
I was talking about discovering parallels.
I'm sorry?
I said, I think I figured out what you're trying to say.
So,
yeah, of course you're right.
Huh? Well, I'm always right.
No, you're not always right. It wouldn't be a computer if you didn't compute things based on dynamically created data. It would not be a Turing machine. So,
but I thought that Skevos was telling us that.
Well, that's not correct.
No, what I said is that we are trying to uncover parallelism.
I'm sorry?
We are trying to uncover parallelism at runtime. Okay, if there is the dynamic data, it's okay, it's not a problem with dynamic data. What is a problem is the way you address those dynamic data. And if you address it with a series of pointers, then it can be done without it. I mean, show me any program, you can just rewrite it in order to be able to discover these things.
But I would say the problem is shared data, it's not dynamism, it's all these complications. It's kind of like functional languages in principle are great for parallelism. They just don't know how to deal with shared data very well. And the minute you actually get to that sharing, which is a very fundamental function of all these systems we're building, a lot of these models don't actually give you the answer that you hoped they would. And that's my concern. I think fundamentally is that related to the shared data structures, the locks around them, how you compose them,
And let me just
what is your systematic way?
let me just go back again to the 90s. Yale said that the data flow machines all were crap. Probably right.
So Yale said what?
That the data flow machines built in Utah and Manchester, they were not working. But all the parallel machines built in the 90s failed. So it's not just data flow, it was just in general. The chip designers were able to give them, the single processor. But sharing data, and actually I'm going back to, there's a paper by David Kansas, retired Fortran, David Kahn, the guy that was doing the size of compiler, retired Fortran, because there was a paper before he was answering. He was able, doing all those things in functional, doing the structures, preserving single assignment, he was able to do better than any compiler on the supercomputers that was running. So it's doable. It just has to do, no one copies data structures. If you copy data structures, if you implement a functional language in the way you copy data structures, the program will not finish. I think the first implementation of SISO didn't do that, and it took months and it was still running. The one program they tried to run. You basically have to count how many they will use a data structure and then reuse it in daily place and things like that. It's easy optimizations. Provided you have enough metadata, you collect them at the same time.
We exceeded the time that was allocated.
So do you propose, Pat, that we come up with a new programming paradigm? What is it? Is it functional programming that would make the discovery of parallelism? And there is some truth in that. If you look at things like MATLAB, it's easier to extract parallelism in that domain than it is if you render the thing. If you hit the produce C button on MATLAB and look at that code, it's so obfuscated at that point you can't see. It's very difficult to analyze it. How are you going to, what would you do in general, not just in a domain-specific way, to have people write things that had somehow exposed parallel, or make it more easy for the hardware to
I think I advocate, what other people are doing also. There's not like one ideal language or something like that. You really have to build layers and in a domain-specific way.
Okay, so
I think it's a very hard problem, but what I think that architects can do is obviously, we will be able to figure out, how to make at least the layer closest to the architects, the efficiency programmers, if you like, make the life easier for them to be more productive. But I don't think we can expose to the big maths out there. One language or something like that.
Okay.
I think
So good. So I was sitting here thinking that maybe we're all wasting our time because it doesn't matter what we put on the chip. The problem is really the software people have to, do what they do and use our chip to do it in whatever best way it is, and we can just go home. It's not an architecture problem. Now Pierre's hit on it. So what do we put on the chip that will enable? So I'll use Pierre's term. What do you say, serious programmer or the
efficiency programmer?
Efficiency programmer. The programmer who knows what the hell she's doing, actually.
Yeah,
as opposed
we
to,
can put it that way.
right, as opposed to the rest of us who have you picked up on that, did you, Chris?
Yeah, I like that.
Yeah, you like that. Yeah.
So atypical.
So what do we put on the chip to enable that to happen, which is actually my hope to...
But it goes hand in hand with what Manolis said about, providing, ways to move data with a bigger, larger granularity or whatever. All these hooks so that this efficiency program can do a better job to leverage on performance out of the chip. That's where we have a big mission as company.
I feel more comfortable if I could see some concrete demonstration.
Well, I can give you a bad example, maybe a bad example. Transaction memory is obviously, I mean, whether that's, going to be useful
But actually,
we don't know.
that's right. It's been a long time coming.
Yeah.
It's an interesting concept. It's been a long
First
time.
paper was
So
ISCA 1993.
what's a long time coming?
Transaction memory.
Well, we're talking about specific things that will open up some opportunities for more parallelism. It's been one of the more popular topics, right, in the last 10 years. And it still hasn't found its way into commercial. Well, I guess the rock had it, right? But,
Yeah, the rock had it.
and what happened to the rock?
Yeah, what happened?
No, it's, another very complicated computer. Is it going to be?
You're asking about hardware primitives that let the software guide the placement or the movement of data. If you're working in a world with scratchpad memories or local memories, it would be remote DMA and the mechanism to notify about the completion of things and wake up specific threads that are waiting for such notifications. If you're working in a world with caches, it would be software guided prefetchers or pre-senders or pre-flashers or something like that.
And do you think that if I put all those things in, it would make the order of magnitude?
It will allow future software on a long-term basis to exploit them for efficiency purposes. It's not easy, but it is a prerequisite. Otherwise, you can do nothing. The software cannot guide something. Or otherwise, it will be the tricks that people are playing with blocking, yes, they call it caches. They write the software so that knowing how the cache is organized, things will happen to come into the cache or stay in the cache.
There's a lot of money in that, actually.
I'm sorry?
There's a lot of money in that. A case in point, if you want to do rapid arbitrage in the stock market, and you do it electronically, and the thing takes a cash miss, that can cost you a lot, literally, millions of dollars. So they spend tons of time figuring out exactly what you would do, how I can lay out my software so it doesn't. From the graduate student, when I was just gave up on academia and took up the job that does that.
Yeah, because computers are trading.
The trading, and they'll take a cash miss, and it's just, you miss the window to trade.
Yeah.
And this is not a joke. It's demonstrably fact. But yeah, that's a specialized thing.
Anybody have anything else?
Would you want to swim?
So before this drags, we should terminate it today, what do you think? What do you think, Yarmo? Will you leave 5 minutes early? Where's
Yes,
Yarmo?
Yarmo is the first question.
He's voting already.
It's on the beach.
So we're,
Yarmo inside.
so we're back to wondering, what are we putting on the chip for primitives? And, or is our job just an education job to get software people to do what needs to be done? I guess I refuse to accept that. I would much prefer that we put the right primitives on the chip. I think it's clear the breaking of the layers we've talked about and get the algorithm people. Manolis just mentioned, if we're talking, we're talking scratchpad DMA. If we're talking caches, prefetching. So maybe we're talking both. Is that what it's supposed to be? And maybe what we should do, go ahead.
Right, one more question.
Sure.
Do you think there is any possibility Well, I'm not sure if it's influenced by economic factors, because in some way, by designing hardware, you can also shape the path of the software people.
So that's what I'm hoping.
What are the chances? No, that's not the question yet. What are the chances that one feature that is not accelerating any of today's applications can end up in a real chip, just with the idea that the software people might make use of it and do better?
It's very high. I mean, that's not how they're intended, right? But, but I mean, chips are full of features that were intended for somebody that then nobody ends up using. And it could take, I mean, you know, in ARM's history, we've had a number of features that we were about to then, you know, get rid of. And by the time we were ready to get rid of it, somebody started using it, and then you were stuck with it. So I think that happens, but it usually doesn't happen for the reasons that you put it in. You always have very high hopes for the features like that.
You don't put it in with the hopes that people can, there's gonna have a major.
No, you put it in with the hopes it's going to have a near-term major reason for it to exist.
Near-term.
Near-term. And then it ends up being that it actually is a long-term one that he's talking about, because it takes people so long to actually move to it.
Ah.
And by the time that feature actually becomes interesting for software, you often find that the hardware has moved on and you wouldn't actually like to support it anymore, because it turns out it's actually quite difficult to support at twice the frequencies that you originally planned it for. So that happens all the time. I can give you a very good example. I'm not sure if you knew the ARM back when it was using the Newton, but there was a feature in it called in the memory system that allowed you. The Newton had this very interesting shared memory structure, which they call them soups. And the way they did it is they introduced segmentation on top of the protected memory. I forgot what that feature was called on ARM. That was done with the explicit purpose of supporting a large number of software people that are trying to do these, you know, sophisticated data structures and still have protection within a single address space. And turns out the only people that ever used it was them, you know, while they had the Newton. Eventually they got rid of the Newton. Nobody else was looking for it, so we wanted to say, well, do you really need this feature in the ARM architecture if nobody's using it? And but by the time we got ready to get rid of it, a couple of other OSs started incorporating it. And it turned out to be a feature that then you had to extend its lifetime for, and it was an OS level feature. And certainly it wasn't used as it was intended, it wasn't even used by the people that used it before. They just have a long lifetime. I think that we tried to get rid of it about 10 or maybe 12 years after it was introduced. And it had one user until then, and suddenly they lost 3 after 11 years. OSs. Domains.
Did you drain already? I think we drained for today.
I think so.
I think we need to do some thinking.
Okay.
Maybe we should do some swimming first.
So in this case, let's thank the panel.